In this lecture, we are going to discuss the relook at the degree of freedom calculation, and I will show you that the calculation that we have done for the degree of freedom of a mechanism, for calculating the degree of freedom of a mechanism, is not foolproof. There are examples where it does not work. Therefore, I call this the failure of degree of freedom calculation. So, I will show you how special dimensions and geometry can lead to failure of this degree of freedom calculation. Then I will touch upon the concept of dead center or singular configurations with some applications. Just to recapitulate, we have done this calculation. The degree of freedom of a spatial kinematic of a planar kinematic chain is given by 3 times number of links minus 1 minus 3 times number of joints plus summation of degree of freedom of individual joints. Similarly, for spatial kinematic chains or mechanisms, we have 6 times number of link minus 1 minus 6 times number of joints plus summation of degree of freedom of all the joints. And I have also told you that a mechanism must have at least 1 degree of freedom, a structure has 0 degrees of freedom, and an over constrained structure has negative degrees of freedom. Now, we will go and look at the failure conditions. Here I have shown you a mechanism, a kinematic chain. Let me calculate the degree of freedom. I will number the links first. So, ground is 1, 2, 3, 4, 5. So, number of links is 5, number of joints 1, 2, 3, 4, 5, 6. So, there are 6 joints, they are all revolute pairs. Therefore, summation of degree of freedom of these joints is 6. Therefore, the degree of freedom of this mechanism or this chain is 3 times number of links minus 1 minus 3 times number of joints plus summation of degree of freedom of all joints. This gives us 12 minus 18 plus 6, and that turns out to be 0. Therefore, even though this chain looks like a mechanism, I mean it looks like it can move, but it cannot. The degree of freedom calculation tells us that it is a structure. So, this is our calculation. Now, this is a structure, but what about this? Here also the calculation remains the same, because I have 1, 2, 3, 4, 5. So, number of links is 5, number of joints is 6, and the previous calculation holds. Therefore, this must also be a structure according to our degree of freedom calculation. According to our degree of freedom calculation, this has zero degrees of freedom, but actually this has 1 degree of freedom, and that is because the dimensions are very special. This length is equal to this length is equal to this length, this length is equal to this length, and this length is equal to this length. Therefore, there are 2 coupled parallelograms in this. Now, what happens due to that? As the link tries to move, the parallelogram structure is retained. Therefore, the equal link lengths, they all remain parallel to one another. Therefore, this is actually a mechanism. This 5 link chain is actually a mechanism, but your degree of freedom calculation tells us this has 0 degrees of freedom. So, this is one case where the degree of freedom calculation has failed. The failure is because of the special dimensions, as I have mentioned. Therefore, due to special dimensions, the degree of freedom calculation can fail. Now, this is an important consideration therefore, because our degree of freedom calculation never takes care of dimensions of the links. Therefore, it can fail because of very special dimensions, as you can see in this case. Now, even though this fails, the degree of freedom calculation actually is a very generic feature. It gives us a very generic feature. Now, what do I mean by a generic feature? A generic feature is one which is not changed under perturbations. In this parallelogram chain or extended parallelogram linkage, as you see in this figure, if I slightly change one of the dimensions or this link length, let us say, suppose I reduce one of the link lengths, immediately this is going to become a structure. It cannot move because the parallelogram nature is lost, the parallelogram property is lost. Therefore, a small change in dimension is going to make it a structure, but when you see this as a structure, a small change in dimensions is not going to change it to a mechanism. If you look at the figure here, if you make small changes in its dimensions, it is still going to be a structure. It is invariant under perturbation. So, therefore, the degree of freedom calculation is invariant under small perturbations. This is a generic feature. This I call a generic feature of the degree of freedom calculation. Let us look at another example. There are two friction discs, just like in gears. Say two gears are in mesh, we can consider the pitch circles as two friction discs, and we know that two gears in mesh can rotate. So, they have 1 degree of freedom. Let us now do this calculation for these two friction discs. So, the ground is 1, this disc is 2 and this disc is 3. So, number of links is 3, number of joints is 1, 2, 3, and summation of degree of freedom of individual kinematic pairs. We have a revolute here that has 1 degree of freedom, we have another revolute here, that is another degree of freedom. So, 2 degrees of freedom. Now, here we have a higher contact pair, there is a higher pair. Now, this higher pair, however, has only 1 degree of freedom because there is pure rolling, it does not allow sliding. This is our assumption, that is it is like 2 gears. Therefore, this only allows pure rolling. So, this has also 1 degree of freedom. Therefore, total number of degree of freedom of the kinematic pairs is 3. Therefore, degree of freedom of the whole chain becomes 3 times number of links minus 1 minus 3 times number of joints plus summation of degree of freedom of individual kinematic pair. So, this becomes 6 minus 9 plus 3, and that tells us 0, but we definitely know that this has 1 degree of freedom. 2 gears can rotate, 2 friction discs like this will rotate. Therefore, our degree of freedom calculation has failed yet again. Now, this failure is due to very special geometry, the circular geometry. So, we have two circles which are rolling over one another. Because of this, the distances between the centers, they are maintained. Let us look at this chain. Here ground is 1, 2, 3. So, here also we have 3 links and 3 kinematic pairs, and degree of freedom of individual is 1, therefore, the summation of degree of freedom is 3, and degree of freedom calculation for this chain is also 0, gives us 0, and we know that this is a structure. Why? Because any small motion, any small tendency of motion is going to change the distance between these two ground hinges. These bodies must extend to accommodate any motion, therefore, motion is not possible. Therefore, in this particular case it is true that it is 0, but because of very special geometry, which is we have these two circles which maintain the distance as they move, therefore, the chain here has 1 degree of freedom. The circles will maintain the distance between the contact and the ground hinges. So, this distance and this distance is always being maintained by the circular geometry. So, because of this, therefore, the special geometry, because of special geometry we have a failure in the degree of freedom calculation. We can have failure of degree of freedom calculation because of another reason, and this is the third situation where it fails. In this example, we have 3 bodies, 1, 2, 3, let me ground this one. There are sliding pairs between these rigid bodies. So, number of links is 3, number of joints is also 3, there are 3 prismatic pairs actually. Individually they have 1 degree of freedom, so summation of degree of freedom is 3. Therefore, the degree of freedom of this chain comes out to be 0, but this can definitely move. Let us see how. If you push this block, this can move in and this moves out, this can definitely move. Now, here therefore, the failure is because of special connectivity. There is a 3p loop, there are 3 prismatic pairs in a loop. Had this been 3 revolute pairs, this would have been 0 degree of freedom, as we have just now seen the previous example. If there are 3 revolute pairs, a 3r loop has 0 degree of freedom, a 3p loop has 1 degree of freedom because of special connectivity therefore. Because the degree of freedom calculation does not distinguish between the kinematic pair, whether it is a prismatic or a revolute. Therefore, because of this special connectivity 3p loop, we have a failure of degree of freedom. Therefore, whenever you have 3p loops, you must add 1 degree of freedom to the total degree of freedom calculation. Now, let us look at a spatial kinematic chain. If you have a spatial kinematic chain, spatial 4R chain, let us look at the degree of freedom calculation. So, number of links is 4, number of joints is also 4. Let me try to draw such a chain. So, this roughly is a 4R spatial kinematic chain, 1, 2, 3, 4. Let me ground link 1. So, therefore, number of links is 4, number of kinematic pairs is also 4. Now, degree of freedom of each kinematic pair, because they are revolute pairs. So, summation of degree of freedom is 4. Therefore, if you do a calculation of degree of freedom of this chain, it turns out to be -2, which means it is an over constrained structure. But let us look at this interesting example, a universal joint. This is a 4R spatial kinematic chain. Let me show you how. This is one revolute pair, this is the second revolute pair, this is the third revolute pair, and this is the fourth revolute pair. Therefore, this is a 4R spatial kinematic chain, and you know that a universal joint does transmit motion, therefore, it can move. So, it does not have, it is not an over constrained structure as this calculation tells you. Now, why do we have failure then? Because of very special dimensions and geometry. Now, remember that there are very special angles here. Now, for example, between these two axes of the two revolutes, it is 90 degree. Between these two axes, it is again 90 degree, and between these two axes is also 90 degree. And because of very special dimensions and geometry, because all the revolute pairs, as you can see, the axis meets at a point. Because of this very special geometry and dimensions, this is a mechanism, and it actually has 1 degree of freedom. Therefore, our failure of degree of freedom calculation, I have once again written them down because of special dimensions, because of special geometry, and because of special connectivity, and it can also have a combination of two of them or of all of these. Therefore, under very special conditions, the degree of freedom calculation can fail, and you have to take care of such pathological cases separately. For example, we have discussed this 3p loop, presence of 3p loop. If you have 3p loops in a kinematic chain, then you must add by hand 1 degree of freedom. So, per 3p loop, the number, if there are more than 1 3p loops, then you must add so many degrees of freedom. So, every 3p loop has 1 degree of freedom. Now, let us discuss briefly, let me introduce this topic of dead center or singular configurations. Here I have shown you an IC engine, and you already know this terminology, top dead center and bottom dead center of an IC engine. Here the kinematic chain is shown in the top dead center configuration. Now, what is this dead center configuration? At this configuration, one of the links is immobile. You may think that therefore, the mechanism has lost its degree of freedom, but actually it does not. here the piston in its top dead center comes to a stop, a momentary stop, as if the mechanism has ceased to move. This link is not moving. The piston at this configuration actually has 0 velocity, it cannot move, but that does not mean that the other parts of the mechanism cannot move. Now, this is the difference between a structure which actually has 0 degrees of freedom and a mechanism at its dead center configuration. Now, this is a very special configuration at which one of the links which was moving might lose motion, as in this case. Yet this has 1 degree of freedom because this crank can still rotate. This is aligned, these two links are the crank and the connecting rod, they are now aligned, and the piston has come to momentary rest. So, at this instant, if I draw something like an equivalent kinematic chain, it looks like this. This is a 3R as it is seen here, but this has 1 degree of freedom exactly at this configuration, not if it moves out of this configuration even slightly. Now, how do I understand this? At this configuration, the crank can either move this way or it can move this way. As the piston comes down, as the mechanism moves out of its dead center configuration, the crank actually has, as a mechanism, it actually has two choices. It can move in the counterclockwise manner or it can go in the clockwise direction. Now, that choice gives us actually a degree of freedom. This choice is the degree of freedom of this kinematic chain at its dead center configuration. Therefore, even though the piston has come to momentary rest, the mechanism actually has not lost its degree of freedom. So, this is an extreme configuration. Now, because of this, you can have arbitrary output speed. You see, the engine can actually be the crank shaft can actually be rotating at an arbitrary speed, even though at this momentary instant the piston is immobile. And there is uncertainty, as I have told you, uncertainty in motion direction, that translates to a gain in degree of freedom, because you have a choice. This is another example of a dead center configuration for a 4R kinematic chain. At this configuration, as you will realize, this link, which I call the input, let us say, this has become immobile. It cannot move any further in this direction. It has to go back. It must go back. It cannot move further in the clockwise direction. It has to go back. Now, as it goes back, the output has two possibilities. Either it can rotate in the counterclockwise sense or in the clockwise sense, as far as the mechanism is concerned. Therefore, you have a choice, and that gives us a degree of freedom, even though the input link has lost its degree of freedom. It has come to a momentary stop. So, again this is an extreme configuration, and the output speed can be arbitrary, and again uncertainty in the direction of motion of the output. Now, this has some interesting applications. This shows the aircraft landing gear. You can see very easily that this link and this link, if you consider these two links as a part of this 4R chain. So, let me draw this 4R chain. So, this is the 4R chain in which this link and this link, they are now collinear. Therefore, this mechanism is now in its dead center configuration or singular configuration. Now, this helps this mechanism to actually take huge loads, and this calculation we will see a little later in this course of lectures. This is another example, the crimping tool. Here also, if you notice, link 2 and link 3 of this 4 bar chain or 4R chain, they are almost collinear. So, this is also very close to the dead center configuration. These are applications of dead center configuration which we are going to discuss, and I will show you through calculations how this configuration is actually very useful in force multiplication. So, let me summarize. We have looked at the failure conditions for the degree of freedom calculation. I have shown you how special dimensions, special geometry, special connectivity can lead to failure of degree of freedom calculation. I have also introduced the topic of dead center or singular configurations, and I have shown you some applications which we will do detailed calculations about little later in this course of lectures. With that, I will close this lecture.